I know it's been a long day and there have been really fantastic talks all day. So I wouldn't blame you if you're really tired, but I promise I'll make it worth your while. So this project that I've been working on is called Kandinsky, and over time, I'm more and more convinced that clustering is tremendous value that we kind of miss, especially in this race to work on large language models and other sort of hot new topic foundational aspect. So what I've started doing is documenting all the variety of clustering algorithms and the pros and cons and the strengths and the weaknesses and so on and so forth within this project called Kandinsky. This was inspired by the painter Kandinsky, and I'll show you why in a minute. So just a quick overview of the repository before I move on to the presentations. Um, I was hoping this would be interactive, but I'll just keep speaking. See my screen, or if you want me to repeat something. All right. I'm happy to take questions in the foyer and the I don't know the Pi Cascades venue list, right? Here, I don't know if we have time for questions, but I have to cover a lot of slides, so I'll move forward, right? So when you get to github.com, this is the repository of the project. I will put it up in the chat. It should ideally be available in the project as well, in the description of the proposal. If not, easy enough to find. Look for Shaurya. That's a really hard name to spell as well as pronounce. I apologize for that. And then Kandinsky, right? And basically this repository, every time I'm making a presentation, I've created a new folder, and you can actually transparently see what was there in the previous folder, and what was the raw and the uncooked versions of it all, right? And the Jupyter notebooks are up front. Just click on it and you see the Jupyter notebook. You should be able to open these in Google Colab as well. I tested this a few days ago, seemed to be working. I may have messed it up, but I'm hoping you will be able to fix it, right? So when we think about clustering, I feel like there's way too many details. For example, not just the basic building blocks, but a variety of algorithms, right? Um, uh, and and depending upon the kind of problems we're trying to solve, we can't just throw one algorithm at everything. You have to keep adapting to things. So eventually the project will have everything, everything that's listed here, but I've started working on it, right? So give me a couple of months. And then this is the main sort of meat and potatoes that I'll talk about where I actually used Kandinsky. So I will be switching between these Jupyter notebooks, all right, and the presentation. If it gets a little too confusing, point that out, please. All right. Okay, here we go. So we're looking at K-means and friends, right? Um, so this is the outline. I'll give you some motivation on why study clustering. Then I'll talk about a movie, and I'll talk about the math behind the most popular algorithm. That's the K-means algorithm, and the method. How do you implement, right? And beyond the implementation, I'll talk about where can we take this forward, right? So let's start with the motivation, right? What are we really talking about here? Um, Look at all the fancy stuff that clustering is essential for these days, right? Look at that. So whether it's image compression, compression or segmenting your customers, dividing them into meaningful cohorts, or clustering your documents. Literally, everybody's talking about RAGs, retrieval augmented generation. But when it comes to document clustering, it is kind of these algorithms, right? And anomaly detection, feature learning, dimensionality reduction, medical imaging, genomics. The list goes on and on and on, right? And here's the last part, which is kind of an unusual use case that I wanted to present to everybody: a movie, right? So early 2002, we were look, 20 years I've been in software engineering, right? I have been looking after machine learning, analytics, and so on. But on the side or on the weekends, I do write and I like photography, right? So those two things came sort of together. And in 2022, we were able to release a completely independently made film, a full feature film called Eight Down Tufan Mail, right? So this was a proper theatrical release in India, and ran rather successfully for a few weeks. So really proud of it. And my role there was I was the cinematographer. Now it looks really stupid, but we didn't have any money to make the film, right? We just had enough ideas to make it. And effectively, what happened was everything that you do in a Hollywood or even in a mid-budget film, you get great equipment, but we didn't have. So here's what we did, right? Um, the best cinematography has exceptional control on color. That's the first principle. That's the one thing that you have to always remember. And I will show you a few examples in a second, right? Um, so here's a couple of instances that really inspired the film, right? I'm going to open up these links here, but they're also available on the GitHub repo. So feel free to so I I do not know if you've seen any of these films, but let me just my God, I'm struggling with my mouse here. Give me a second. Right. So these are the films that we kind of uh, aspired to when we were thinking about shooting the film. Right. So this is the kind of image that we were going for when we were making the film. You can, of course, see that it has exceptional control on color. You have this one beige background, this blue-gray dress, the gold, the skin, and that's it. It doesn't have like a riot of colors. It has very limited colors, and every color means something, right? And if you look at any part of the film, that's how this is working, right? Literally any part of the film. So the same goes for a bunch of other ones that we really liked. Um, I think the Passion of Anna is really really interesting from an example. Um, Look at this one. The two colors you notice are the blue eyes and the red scarf. That's just fantastic cinematography, right? And you can just literally pick any shot and you'll say, all right, I can see that they are controlling the color really, really well, right? Do you know what I mean? So let's one more example and then we'll move on to the other bit. Let's look at after the rehearsal because it's a very sort of unassuming but fantastic. Look at the control on this one, right? Color control on this one is right something that you like literally write home about and say, "Oh my God, I don't know what I saw today." Right? Look at the color control on this one. They know exactly what each color is saying, right? So similarly, my director also had meanings to each of these colors. So we're saying we're going to use one color, two color, or a few colors, but no more. We don't want to, like, we don't want unnecessary colors to pollute the meaning of the scene, right? And the director, like I said, is ascribing meaning to each one of these things to create a story around it, right? And they must remain approximately consistent, right? So the colors that we see are different from the voltages that get excited in the camera sensor. And it's different from the voltages that get excited in a computer screen versus the voltages in a television screen versus the voltages in a projector in a cinema hall, right? In a theater. So what you have to do is, hey, there's a certain kind of red that we have ascribed meaning for, um, and it kind of has to stay the same, right? Similarly, uh, no matter what happens to your image or what kind of device, the relationships between those colors should be approximately consistent, right? Um, or else. So I am hogging, I think, into right. So, I had a great director and a very, very, very dedicated team. So use your imagination. What else could have gone wrong had I not worked hard enough on making the colors consistent, right? Um, so in Hollywood and in actual professional filmmaking, there are really expensive cameras that help you do this, and there's a lot of software, a lot of control processes that are in place. In fact, Academy of Motion Pictures Arts and Sciences, they themselves have created a standard that mostly people follow, right? Um, this stuff costs between a few hundred to a few $100,000 every day, right? For the entire film, we shot for about 10 days. We had $359. I'm not even joking, right? Um, so effectively, I had to kind of hack this, right? So the Python engineer comes out. So, like I said, light can be thought of as waves, and waves have wavelengths, right? And those wavelengths resolve into colors, right? So the long wavelengths resolve into red and red light colors. The medium ones that we see the most resolve into green and green light colors, and the short ones into blue and blue light colors, right? So how do you pick the colors? Because we're not looking at a single wavelength of light when we say, oh, I need that deep sky blue with a tinge of pink in it. We're looking at a complex thing. So how do you pick these colors? So I used an algorithm called KMeans plus plus to do it. The plus plus part we'll discuss separately. The plus plus part basically means we have a special way of initializing the algorithm, but that's about it, right? Um, and I want to show you how. But right before that, I want to show you some of the images from the film and show you what we're doing to set our experiments up, right? So this is the first notebook. Um, Look, I can't see chat or anything, so please speak up if I'm missing something. All right. So the first thing we did here was we'll just import all of this stuff. Is is just literally display these images in our notebook. I think I should do it in Windows because that might be a slightly more interesting visual. All right. So these are actual screenshots from the film, from the finished product. I actually took them from the YouTube print. We've now posted the film on YouTube after a year. So I actually took this from YouTube. So no manipulations, right? So these are individual shots from the film. And again, I hope somebody can recognize that there is a measure of control on color. Of course, not as good as the Polish films we were looking at, or the Russian films, but there is a measure of control, right? Um, right. So that, I'm just being straight. It's just literally a YouTube screenshot, right? So the same things, what we've done is rendered in our Jupyter notebook. And then we want to extract this data and create our data sets. So what I'm doing here is I'm using the OpenCV library to store these images, which are in the red, green, blue color model, store them in a variety of models, right? So if you were to go inside Kandinsky, once you run this notebook, if you were to go into the data folder, you will actually see the individual CSV files, right? So for every image, we have now converted this into different ways of representing color on a computer, right? So hue, saturation, lightness, hue, saturation, value, LAB, RGB, XYZ. These are different models of representing color in a computer system, right? So all this notebook is doing is that it's just taking each one of those images and processing them into each of these models, right? I hope that made sense. So let me go back to the PowerPoint slide. And let's look at how the algorithm itself works, right? And almost all the algorithms, whether it's density based or even more complex ones, effectively follow the same script. So imagine, and I'm trying to do a very, very naive explainer with no formulae in them, right? So please, don't feel that, oh, there's a lot of math coming up, right? So it's super easy. In fact, it's literally just one-liner explanations all over. So imagine you have a bunch of marbles, right, just scattered around, and you want to club them together like we did. We have pixels. So imagine each pixel is a marble of a certain color, and we want to club all the colors together, right? Um, so here you can see that approximately two groups are forming. One's a yellowish group, one's a cool group with blue and blue-like colors in it. So the K-means method is basically deciding, hey, we're going to group the marbles based on something. We could have grouped them based on transparency. We could have grouped them based on size. We could have grouped them based on something else, the impurities in the glass, whatever. We're right now trying to group them based on color, right? And then the K in K-means is effectively saying, here's how many groups I want, right? So imagine somebody who's really a painter. They can actually create hundreds of groups. Like this is slightly yellow, this is slightly orangish yellow, this is right. So they can keep creating more and more groups, but there will be an ideal number above which or below which the model is going to be ineffective or slightly less effective, right? So that's the whole trick in K-means. K, in certain cases, you will hear the word hyperparameter being used. It needs to be tuned, right? You need to find the right number of clusters for your data set. And this K, I'm sure you can imagine now, is what we were chasing when in a given scene, my director said, I'm looking at maybe 4 or 5 colors here. And I had to kind of take a shot, quantize it, K-means, and say, all right, these are the 5 colors we're really focused on, right? And then all I had to do was track those colors across the process to ensure these 4 colors are consistent. So the family of colors around them would automatically follow, right? So I'll show you the examples in a minute. But here's basically the 4 steps to any clustering approach. You initialize, you assign, you update, and you repeat. right? So let's look at the initialize. Literally at random, select however many clusters you want to create. You want to create 3 clusters, select 3 points at random. If you were to select these 3 points based on a distribution, it would be k-means plus plus. That's the actual algorithm we used in the movie. But right now, just naive explainer, just at random, select however many points you want. For each point, select the closest points to it, right? So calculate the distance of all the points from this one, and select all the points, cluster all the points that are closest to each centroid, right? Very easy. I know it's compute intensive, but it's a super easy step. Update. Now the clusters that you have, they may not be the final clusters. What you can do is you can look at this cluster, find out the mean of this cluster, and make that the new centroid, and just repeat. Again, assign based on the new centroid. You have new clusters, figure out the new mean, then assign again, and then so on and so forth. Keep doing that, and you'll see that the centroids kind of move towards the ideal naturally occurring clusters, right? So the algorithm mathematically is guaranteed to converge, which means if you let it run long enough, it will give you the centroids. But in practice, what happens is that the centroids kind of circle around the actual point, right? So the centroids keep dancing around. So we have to implement a limiting function. We have to say, okay, we'll repeat it 10 times, and then whatever the cluster will be done, right? So we end up implementing a limit, right? So I would like to now quickly show you. Actually, let's just finish these slides, and I'll actually walk you through the oh, there's messages in the chat. Okay, so I think my time is up. Let me just quickly show you the notebook, and I'll be done. All right. So we're loading the data in the image and in the that I just showed you. So right. Here's this really quick, simple implementation of k-means. So if I do a Shift L, it's literally 20 lines of code, right? Super easy to implement. And then when we test it on images, I can show you this was the original screen. It literally is just 3 colors. All I had to do for the scene was track these 3 colors. One of them is black. Super easy to do then. This is a 4-color screen, 4-color scene. The shot has literally 4 colors that I have to track. And using k-means, I could then easily find those 4 colors. You can see that the colors represent the ideas in the scene really, really well. The same goes for this one. This surprisingly simple looking shot has 5 colors, right? Similarly, this one is supposed to have 3, but it had 4, I think, or 5. All right. So this surprisingly simple looking shot, again, very colorful. And this one is actually practically a monochromatic shot, which I think I can show you here, hopefully. Or let me not waste time. But this was practically a monochromatic shot. By that, I mean, you're looking at warm tones, and then you're looking at shadows. That's it. So we were able to really, really successfully deliver a film right out to theaters thanks to k-means and clustering. On the repository, I have put up the links to the film as well. So you can go ahead, watch it on YouTube. I can open it, hopefully. And there you go. You can actually watch the entire film. On YouTube, it's got English subtitles and everything, right? So hopefully I'll get some feedback there as well. This I know was slightly rushed. uh, but is K-means. There is a lot of other detail that I am putting up in the repository. Please join me there. I do not have anything else to present. If there are members in the audience who would like to talk or who would, I don't know, if there's no questions, we can wrap up.